And we, again, now that we have those input files to AutoDock Vina, and what AutoDock Vina needed is a PDB-QT file of our receptor structure, our ligand structure, and to make that PDB-QT file, we had to adjust everything and add our hydrogens. So now that we've done all that, we can feed those structures into AutoDock Vina. Okay, so in this notebook, we're going to actually be looking at running that docking calculation with AutoDock Vina. We're going to be visualizing the results from those docking calculations using a Python library called prolif, which is for protein ligand interface. I think it's something like that. I've got it later in the notebook. Okay, so we're going to be learning how to execute ligand docking using AutoDock Vina. We're going to be defining a ligand box for docking. So in order to dock something using AutoDock Vina, we have to tell it what part of the protein we want to dock to. And then we're going to analyze and interpret our docking results using a library called prolif. So in this particular case, when we're docking, we already know where the docking pocket is going to be. We're going to base it on that experimentally determined structure. We have a structure with a ligand bound already, so we know where we're trying to dock. We did have a question a very good question in the Discord during the break on sort of what if I don't know where I want to dock, or how can I find alternate docking locations? So there are libraries out there that exist that can analyze protein structures and find potential binding pockets. But we're not addressing those today. We're just going to take a binding site that we know already. So molecular docking, it simulates the interaction between a small molecule and a protein, and it predicts how the molecules fit together at the molecular level. It's really commonly used in fields such as drug development to design molecules to bind enzymes or proteins. During this docking process, what's going to happen is we're going to tell AutoDock Vina what our receptor is, that's our protein. We're going to tell it what our ligand is, and then AutoDock Vina, and then we're going to tell it where we want it to dock. So we're going to define a binding pocket. And then AutoDock Vina is going to take that ligand and it's going to try various orientations and conformations of the ligand within the protein's binding pocket. And for each pose that it tries, it's going to assign that pose a score. And that score is going to be based sort of on some scoring function that's been predefined. So those functions can be things like physics-based, so they can be based on force fields, for those of you who have worked with force fields before. They can be empirical. And so we're going to be using a scoring function called Vina, or Vina. You can switch it out, but AutoDock Vina has 3 scoring functions that it can use. 2 of them are empirical. We're going to be using one of the empirical ones. And there's even work that's done to make things like machine learning scoring functions to predict binding affinity. I did include a link if you're interested just in information on scoring functions. I did include a link to a recent review on scoring functions. So that's what we're going for. And so the libraries that we're going to use for this notebook, we're again going to be using OS for handling file paths and directories. We're going to be using MD analysis again to measure things about our structure. So we're going to be using MD analysis to help us define that binding pocket for our ligand. We're going to be using Vina for this is the AutoDock Vina Python API to actually do our docking. And then we're going to be using a library called prolif, which is for protein ligand interaction fingerprint, that generates an analysis of the different types of interactions that are going on in that binding pocket once we've done the binding. Okay, so before we dock, I mentioned that we have to define the place on the protein structure that we want to dock to. So we have to define our actual docking ligand box. There are different ways that you could do this. Because we have a structure that has our ideal ligand docked already, we are going to use the location of that ligand to define the binding pocket that we're going to be docking to. So if I were to look at my docking preparation, I'll just remind you of the structure that we looked at. We're going to define our binding pocket by this ligand that's already bound in our starting structure before we isolated anything. So we're going to be docking to this same location. So we are going to load that structure. You'll see here, this is that PDB that we downloaded from the protein data bank. We're going to load that structure into MD analysis, and then we're going to select just the ligands. And then we can use functions in MD analysis to calculate where that ligand is in order to define our binding pocket. So here we're reading in that PDB, we're selecting the ligands, and here we're going to use a function in MD analysis. So we'll give it ligand MDA. And that is the name of my ligand selection. And then I'm going to get the center of my binding pocket by just finding the center of geometry. So in order to define where we're doing the docking, Vina needs two pieces of information. It needs the location of the docking box center, and then it needs us to actually tell us what the box is. And this first step, we're taking the location where our ligand is already bound, that center of geometry, to be the center of what we're going to do, consider our binding pocket. So again, I did that just by putting it in MD analysis, and I'm using an MD analysis function called center of geometry. And then I've got that printed here, so I can print what that is. And so this tells me the 3D coordinates of the center of my binding pocket for my docking. Okay, so after defining the pocket center, we're going to define what the actual ligand box is. And we're taking kind of a simple approach to defining this ligand box. We're just going to take the minimum and maximum positions of our ligand in each direction and subtract them to get the size of our ligand box. And then we're just going to make it a little bit bigger by adding a 5 angstrom buffer around the edges. So you might choose to define your binding pocket differently. For our purposes, we're just defining it in a very simple way to be the min and max of that already bound ligand, and then just adding a little bit of buffer to that. So we'll add in here, we had ligand box equals ligand MDA. Here is how we can get the positions of a particular atom group. Then we take the maximum. We will want to subtract the minimum. So we'll change this expression a little bit. Ligand NDA dot positions dot min. So here we're taking the minimum coordinate of the ligand in each direction. And that's going to give us a particular, so if I just ran that, that's going to give me a particular box size. So this tells me that my ligand docking box is 9 units in the X direction, 12 in the Y direction, and 8 in the Z direction. But I'm just going to make it a little bit bigger by just adding 5 to it. So this just adds a little bit of a buffer to each side of our box to make our binding box a little bit bigger. So maybe if we're doing our docking calculations, if we make it too small, it's not going to be able to find, there might be some binding that we might miss. So we're just going to make it a little bit bigger. Okay, so far we have used MD analysis to calculate our center of geometry of our ligand. And we've used MD analysis to calculate the size of our ligand box by just considering the min and max coordinate of our ligand. And this last step here, we're just converting those NumPy, these that we've calculated, those are NumPy arrays. AutoDock Vina just wants them to be lists. So we're just going to use this toList method to make sure that what the variables that we have to input to AutoDock Vina are lists and not NumPy arrays. So I'm going to fill in the ligand box to list. It's not going to do anything about changing the numbers. It's just going to change the data type. The data type. of those variables. Okay, so we're preparing for docking. In order to dock, there are various pieces of information that we needed. We needed those PDB QT files that we created. We also needed to define where we are docking on our structure. There are different ways to do that. We chose to take that ligand that's already bound. So now that we have those pieces of information, we have our input files and we have our binding pocket. We are now ready. We're finally ready to do our actual docking calculation. So this, in this cell, we're going to get ready to do it. So we're doing a little bit of file management here. We're going to make yet another folder for just our docking results. And we'll do, this is the function that we've been using throughout the workshop to make directories. And I'm going to make a directory called docking results. And again, I'll tell it if it exists, that's okay. Okay, so I'm making a directory called docking results, and I am going to store my docking results in that directory. I like to keep things very separate. So, at each step here, we've had different directories for different things. We'll make that docking results directory just for the docking results. And now that we have our directory, let's actually do the docking. So for the docking, we're going to import our Vina library. For the Python API, we do import Vina from Vina, import Vina. And then we create our docking object. And when we do that, we give it a scoring function. So here we're giving a scoring function name. We are going to be using the Vina scoring function to do docking in this case. So here's a little bit more about the scoring functions that are available in AutoDock Vina. Remember what the scoring function is for is it is the equation basically that is used to determine the interaction energy of our ligand with our protein. So what's going to happen when we do this docking is it's going to try a bunch of different poses, and it's going to calculate a scoring function it's going to calculate a value depending on the scoring function that we pick. And we're going to pick Vina. I'm going to say a little bit more about, I'm going to come back and say more about scoring functions while we are waiting for our calculation to run, because we're actually going to see that the docking calculation is a bit compute intensive. So let's just execute this cell. This is setting up our docking object, and it's telling what scoring function we want to use, which is the Vina scoring function. After we do that, we need to set up what our receptor and our ligand is. So we need to tell it what protein we're docking to, and then we tell it what ligand we are docking. So initially, we are just going to redock that ideal ligand. We're not going to dock the modified ones until we dock the original one first. So to do our docking calculation, we'll want to set our receptor. And here we're setting our receptor to be that PDB file that we created. Now we're going to set our ligand. And we had set earlier, I've set my ligand 13U in a variable. So initially we're going to set our ligand to be we're setting it equal to that ideal ligand. And then we want to set our docking location. So we're going to set that pocket where the pocket center is, as well as the pocket size. So we calculated that already. And that was in a variable called pocket center, and also in a variable called ligand box. So those were things that we calculated at the first part of this notebook. So this is computing some maps that are going to be used later. Okay, and after we set that, we actually perform the docking. So here is the step that does the actual docking. There are two, I'm going to go ahead and execute this. You can go ahead and run it. There are two parameters for this docking calculation. There is a parameter called exhaustiveness and then number of poses. And so we have our exhaustiveness for, you're going to see that it takes a little bit to run here because it's actually doing a docking calculation. And what it's doing is it's taking that ligand and kind of fitting it onto our receptor and doing and scoring it. So you can see that it's still running. So this exhaustiveness basically says sort of how many poses are going to be tried. A higher number is better for getting you more docking results or better docking results. The default value for exhaustiveness in AutoDock Vina is 8, but they recommend in their docs for best docking results to use something like 32. So that is much higher than we want to set it right now, because if we set it higher, we're going to be waiting for several minutes. But what that means is that the poses that we see might not be that good. So if you were doing a real docking calculation, you would want to set this exhaustiveness to be higher. We're also only writing out 5 poses. You would probably want to write out significantly, well, maybe not so, you would want to write out more, again, if you were doing an actual docking calculation. But again, for the purposes of this workshop, just so we're not sitting here a very long time, we've left these numbers relatively low. To say a little bit, I said I was going to say something about scoring functions. So we're using AutoDock Vina. We're using AutoDock Vina, and one thing about AutoDock Vina is that it has 3 scoring functions. If you want to use different scoring functions, there are other open source docking softwares that you can use. So, for example, one popular one where the scoring function is more customizable is one called Smina. And for Smina, you can set a more custom scoring function. But ones that are available in AutoDock Vina are the Vina scoring function, which is one that we're using. This is an empirical scoring function where we have different terms like hydrogen, hydrophobic interactions, and steric interactions. The scoring function was empirically derived from putting data available in the PDB-bind database. I've linked you to the original publication as well as the paper for the next scoring function that's available as part of AutoDock Vina called Vinardo. And this is for Vina radii optimized. It's to develop the scoring function by adjusting atomic radii of the original Vina function. And then AutoDock Vina also has a physics-based scoring functional available called AD4. This is the most computationally intensive scoring function that's available in AutoDock Vina, but we can't use it for our system because it requires the definition of a flexible receptor. So we would have to go through some additional preparation if we wanted to use this scoring function. But these are ones that are available if you are using AutoDock Vina and have prepared your files. So I've talked through the scoring functions, and now I'm checking. So my docking is still going. I am seeing in the Discord that some people's docking is finished. So hopefully mine will finish soon. I will comment that my computer is running significantly slower with Zoom than it usually does. So I think that that's an issue that we're encountering. And yes, I am running locally, and it usually runs much faster. So many people are saying in the Discord that they are docked and ready to go. So let's pause here for another minute.
I did mine in CodeSpace and it finished about 2 minutes ago.
Right. Yeah, I think that it might have something to do with sharing the screen for me.
Yep.
I may stop sharing for just a moment to see if that helps. Apologies. Paul, could you perhaps share? Should we keep waiting for mine, or
Let's give it another minute, and if not, we'll switch over to my screen. You can just
tell you what to type? Okay.
tell me what to type. Yeah. Maybe for these computationally intensive portions, we should have the Martha Stewart method where we've already got the cooked cake ready
Great
to.
idea. You know what? It finished. Great. Okay, I'm going to share my screen again.
Okay, good.
Yes. And I'm getting a very bad thunderstorm where I live, so I don't know if everyone's going to start hearing thunder. But okay, so mine has finally finished docking, and it's also like, thank goodness I didn't choose something more computationally intensive, right? So I've experienced this with AutoDock Vina in the Jupyter Notebook. It always gives you this little output here that says 100%. Depending on whether it feels like it or not, it might also display the energies for you. But luckily, we can just access those in case it doesn't, as in it hasn't now. So once your docking calculation is finished, we're going to go ahead and write out your results. So AutoDock Vina, again, it writes these PDB-QT files, and it's going to output just the structure of those ligands that it docked. So for the ligand, it found 5 poses. Did everyone? Never mind. That was just
Yes.
a thunder.
Yes, we heard it. Just a little bit, not much.
So for those poses, we have four poses. We're going to write them out as a PDB QT file in our docking results folder. So I'm going to run that. It should run pretty quickly, but now we have a file with all of those poses saved. So if you would like to see the energies that were calculated for your poses, we can see that by doing v.energies. So this is going to give us a NumPy array where we have the energies that were calculated for our docking poses. The first column is the overall score for each pose. So our top score here had negative 5.22. And then these other columns correspond to other types of energies in the docking score. And so these are dependent on the the scoring function that you use. But for the Vina scoring function, these correspond to the total energy, the inter-energy, intra-torsions, and then intra-best pose energies. And I'm actually not quite sure what this last one is, but that's what each column in this is. And you might wish for your particular docking calculation. So I'll also comment that when it does these docking calculations, there's a random component to it. So each of us are going to have slightly different numbers that we see for these docking energies. And we're each going to have also slightly different poses that we see for our docking poses. So if we want to save these energies and return to them later, I'm going to use pandas for that. So pandas is another library that we covered in a previous workshop that's good for working with tabular data or CSV files. And since I did that docking calculation, and especially since it took me so long to do it, I want to save those energies in a file. So I'm going to import pandas here. I'm giving it the energy names. And if you are curious how I knew what those energies corresponded to, I read the documentation for the software. That's how I know what the different terms are. I'm just having a name for my columns, and I'm going to create a data frame here where I put in the energies, and then I'll put in my columns. So now I have a data frame with my energies, and I'm just going to save that in a CSV file so that I can refer to it later if I'd like, because I have the actual configuration of each pose saved in that PDBQT file. I might want to know the energies that correspond to each of those poses. So I'm going to save that as a CSV in my docking results folder. And I'll call it 13U energies.csv. Okay, and now if I go to my docking results folder, I'm going to see that I have the poses for that first ligand, as well as the energies saved as a CSV file. Okay, so now we want to actually visualize our docking results. So after performing the docking simulation and saving the energy, we want to look at the poses. So when you visualize results from molecular docking, scientists are often looking at both the 3D dock structure, the 3D structure of the dock ligand, as well as a 2D representation called an interaction map. And so an interaction map is something where we have our ligand kind of represented as a 2D structure, and we have a map of the binding site of the residues that are in the binding site. And then we have annotations of the types of interactions that the ligand is having with residues in that binding site. And so we are going to use a library called ProLif in order to create both of those visualizations. So this is more fun with file formats. AutoDock Vina outputs a PDBQT file, but if we use ProLif, it wants our small molecules saved as an SDF. So we are again going to use Miko to take our PDBQT files and convert them to SDF. And Miko fills in very, very nicely to ProLif. That's one reason that we're using it. But you should note that if you want to convert PDBQT to SDF using Miko, you need to make your PDBQT with Miko originally. So that's why I used Miko in the last one. So we're going to use another command line script from Miko called mkexport. And so we're exporting our PDBQT of our docking results to an SDF file. So I'm going to run that. And if I just take a peek again at my docking results folder, I see that I have this SDF now of my docked ligands. And now I can do my analysis with ProLif. So I'm importing ProLif as PLF. And then I'm importing MD analysis as well, because I'm going to use MD analysis to load in my protein structure. And again, for ProLif, that's another place where we want to use our structure with the hydrogens, because ProLif does an analysis of the interaction. It needs the hydrogens attached, just like AutoDock Vina. So we are loading in our protein file, our protein structure with our hydrogens. And then after that, we are going to load in our structures. So right now we have our structure in MD analysis. Next, we need to load it into ProLif. So we are loading our MD analysis structure of a protein into ProLif with molecule from MDA. And then we can just put in that SDF file from Miko. So that was in docking results 13u.sdf. And this is the file that we just created in this step. So that loads our structures into ProLif. And I promise I usually don't have to wait for this, but I'm waiting on my code to execute.
So Jessica, at this point, just to be clear, the docking's been done.
Yes, the
And we're just
docking is
trying
done.
we're trying to look, we're finding different ways to look at our results.
That's correct. So we did the docking. So we did the docking in the previous step, and then we wrote out. So when we're doing docking, we're getting those scores from docking, and then we're also getting our docking poses. And so we did the docking with AutoDock Vina, and we have written out what our poses were. AutoDock Vina writes out as a PDB-QT, and then we had to convert that to an SDF. And now we're just taking our results. We've done our docking calculation, and this part with ProLif is just viewing our results. So we want to look at what these poses actually look like. So here we calculate a fingerprint. This tells ProLif the types of interactions that we want to analyze. Here we're not putting anything in, so it has the default interactions, which are these listed here. It has a number of different interactions that you could analyze as well. If you'd like to see what those are, I would refer you to the ProLif docs. It also allows you to define your own custom interaction types if you would like, but we're just going to do the default analysis for the types of interactions we'd like to analyze. So now we need to actually fill in. Here we have our poses read into ProLif. We need to tell it to actually run on those poses. So we'll pass in our poses structure. Then we'll pass in our protein structure. And so this is telling ProLif to actually analyze our poses. So this runs pretty quickly. So if you had more poses here, it would run on all of them. We wrote out 5 poses, so it is analyzing those 5 that we read in. And you can see that, as I mentioned, it's analyzing 5 types of interactions. It's going to analyze our hydrophobic, H-bond acceptor, H-bond donor, cationic, anionic, then some pi interactions for each of those poses with our protein. So it takes in the poses that were output from AutoDock Vina and the protein structure, and it analyzes sort of what types of interactions are happening with each pose. So this is just a variable, a convenience variable. I'm going to say we want to look at the results from our first pose. And then we can use this function in ProLif called plot lig network. I'm going to execute that. And this may take a moment to appear, but you will get a 2D representation like this that shows here is our ligand. And then here are the residues that are in our binding pocket. And these dashed lines represent the types of interactions that our ligand is having with residues in our binding pocket. So if we scroll down, you'll see a key. So our acidic residues are colored in red, aliphatic are colored in green. Then we have aromatic residues in purple. So here it's coloring by the type of residue. So we have the label and the type. And then the color of the dashed line indicates the type of interaction that is being calculated. And this figure is interactive. So for example, if I wanted to get rid of the van der Waals and the hydrophobic interactions that were found, I could just leave H-bond donor highlighted, and I could see that I'm seeing that type of interaction over here. Or you could look at just particular types of residues in this view if you wanted. Okay, so this is kind of looking at what's going on with the first pose. If I wanted to change to the second pose, I could change this number to 2. And it would show me the results for that pose. So it's going to be slightly different than what we saw for the first pose. Okay, I'm going to change back to 1 just for our best pose that we found for this particular docking calculation. And again, your calculation is going to be slightly different, so your map will look probably a little bit different than mine. And then using ProLift, we can also do a 3D plot to see how this ligand is bound in our binding site. So here is a 3D plot of our docked ligand along with its interactions. And we had a question in the chat about the lowest binding energy translating to the best pose. So yes, typically that does translate to the best pose, but we are all going to see slightly, just because of the way the docking has performed, we're all going to see slightly different poses and interactions. And not again, but we have that exhaustiveness parameter set to a low number just for the purposes of keeping the calculation reasonable for this workshop. But if you were to increase that, you would get better results. So if you want to increase that, like kind of ramp that up to something like 32 or something higher, they're going to maybe see, because I see some of you aren't seeing any H-bond donors, you'll likely get better results if you increase that exhaustiveness. Okay, and so there is a lot more that you can do with ProLift. So you can, for example, save the interactions as a data frame, or there are other visualizations that you can do. I would just encourage you to check the documentation for that. Okay, so as a final exercise, I would like for everyone to try to dock one of our modified ligands so that we can do a comparison. And then as far as, so we had a question about downloading the results of the poses and opening them in PyMol. Yes, you should be able to do that. PyMol may be able to work with PDB-QT files, but it might work with SDF. But yes, you should be able to download them and view them in PyMol. Okay, so that's the end of this notebook. Let's take about 10 minutes here for everyone to try doing another docking calculation using one or both of our modified ligands. And then we can come back and talk about that and then wrap up. So we had 2 modified ligands to dock. We had one that had a nitrogen and that aromatic ring, and then one where we had added a methyl group. So you could have chosen to run both or either. I went ahead and did the methyl group. So here I've changed the name of the ligand I was docking. I made another Vina docking calculation. I set my receptor and ligand, this time to my modified methyl ligand, used the same pocket center and binding box, and then did my docking. And here are the results that I got. I wrote out my poses as well as the energies, and then exported those using the same procedure that we had before, and then ran my analysis. So if I look, and again, if I look, I can see that I now have this methyl group. I've got some different interactions. I think if we were to compare the map, the interactions look a little bit different. And then if I look at this, so mine looks kind of funky here, but we can see that for mine, it's sort of like folded over. It's not really in that binding pocket anymore. So maybe you've seen that, but this could be the effect of like not having a very high exhaustiveness, or that the ligand has changed. But here's my result for the ligand with methyl added. So it is quite a bit different. All right, so that is the end of our notebooks. And I think we can take some questions and then do whatever we need to wrap up from here. So maybe
Yes,
we can,
certainly.
yeah.
There's a question about why the affinity values are varying for different people.
So the affinity values are going to be different for every person, because what AutoDock Vina is doing underneath when it does the docking is it's using a process that has some aspect of randomness in it in order to generate the poses. So what that means is that every time you do a docking calculation, or if you compare different people who've done the docking calculations, everyone's are going to be just slightly different. So that's why people are getting slightly different getting different numbers for the docking.
There's a question about the dashed lines. Are all the dashed lines the interactions? Yeah, it's finding, and
Yes.
they
Yes.
are. And if you mouse over them in the video or in the screen, you'll see that it'll identify it as a van der Waals contact or a hydrogen bond or something. And then somebody comments that some of them look really long, like too long to be important.
Right. That's a good question. So for each of these, if we were to check the documentation for ProLift, they have a certain radius that they check within. So if you wanted, so right now we're just using the default values for distance where it analyzes, but if you wanted, you could adjust that if you felt like it was too long.
There's a question: when docking to a new protein, how do you estimate how good a given affinity is?
Um, when we say how good it is, I think that there are a lot of questions about that. So sort of like, what does docking score actually translate to? So docking gives you an idea of comparatively, I think, what is a good score for a particular ligand, but then there's some question of how different scoring functions and different docking calculations actually translate to the real world. So in some ways, that's kind of an open question. Docking is usually just kind of a first step for getting an idea about how a molecule might interact with a receptor.
I actually watched the video by the folks who created AutoDock, and this was probably 5 years ago, but they said that they assume that a value that's given is within 2 orders of magnitude. You know, so a score of -5 could be somewhere between -3 and -7 in terms of the energy there. And that's why they encourage you to do 32 exhaustiveness things to try to get that to get a better value. Because I mean I did the methylated one and my values were off by about 0.3 from yours.
Okay.
I've asked Levi to post the link for the exit survey on Discord now. And I'm not telling you to stop asking questions, but if you're about to leave, please hit that now. There's almost 400 people left in the room, and we would love to get all of you to give us feedback because you've been here for the whole time. Thanks for doing that, Levi.
Yes, please fill it
You're
out.
welcome.
The
Yes.
question is, will the GitHub resources stay up? Absolutely. We're going to
Yes.
leave those up indefinitely. And so that once the recordings of this workshop are up, people can go to those recordings and use the same link to go to that IQB-2024 folder and use it.
Yes.
Well, here's a good question. What are good academic practices you would like to see taken up more?
Data management, good data management. And then also at Mulsey, we're a big fan of open source software and open science in general. So what we like to see is when you publish papers, we like to see you publish enough information for your calculations to be repeated. So that might be publishing structures as supplemental information, as well as publishing code that you use to do a particular calculation. So that can be done through, things like GitHub or Zenodo or supplemental information. That's my answer on academic practices that I would like to see more of. I don't know if other people have other.
I think for me, particularly if you're going to share a Jupyter notebook with people, don't just put the code in there. Document it. For every code cell, there should be a markdown cell explaining what's coming up, or at least some comments in that code cell explaining what's it about. And that'll be very helpful for me, I think, for everybody.